The question that I have is, could you explain how to analyze a frictional journal bearing? If you recall from our introductory video on friction, this is one of the problems we were going to discuss. I have added a cat picture to make it a little bit more real. Basically, a cylindrical shaft is supported in a cylindrical hole like this. The shaft is called the journal and the supporting element is called the bearing. The shaft is subjected to some kind of torque. This is generally used in conjunction with a rotary machine where the shaft is spinning. All contact surfaces have friction, right? This is no exception. There's going to be friction between the shaft and the bearing along this contact surface. What exactly is the contact surface? Well, that depends on the torque and the other forces acting on the shaft, and we'll discuss that in the next few slides. Because of this friction, you have to apply a minimum torque in order to rotate this shaft. So this is the torque that is needed to overcome the resisting torque emerging from the frictional force. If the shaft is spinning at a constant angular velocity and if nothing else is acting, this torque must balance the torque coming from the frictional force in order to keep the shaft spinning at that constant velocity, right? There are several kinds in this, including plain bearing, which includes journal bearing, sleeve bearing, etc. Rolling element bearing, which includes ball bearing and roller bearing, fluid bearing, magnetic bearing, and so on. So these are different styles, and some of which are designed to minimize the friction. For example, ball bearing, right? So the ball bearing minimizes the friction. It brings it down to a minimum level. The analysis of these different types are similar, so in this video we'll just stick to plain bearing. Another similar system is a pulley that spins on a shaft like shown over here. The theories we developed for a plain journal bearing can be applied to this as well, so we'll do that. Let's go ahead and analyze a plain journal bearing. Let's start with the situation where the shaft is subjected to vertical force P like shown in this picture, but not a torque yet. Let's say the shaft sinks down a little and makes contact with the bearing at point A. There's going to be a force reaction at that contact. Let's say the reaction between the bearing and the shaft is R. Since the shaft is not subjected to a horizontal applied force or a torque, the equilibrium equation in the vertical direction says this P must be equal to each other in magnitude and opposed in direction, right? Therefore, if P is vertical, R has to be vertical, and these 2 points, points C, which is the center of the shaft, and A, which is the contact point between the shaft and the bearing, must be on a vertical line. Now let's consider a shaft with a torque. Remember in the earlier slide we said if the contact between the shaft and the bearing is frictional, you have to apply a minimum torque in order to rotate the shaft, right? The torque that is needed to overcome the torque due to the frictional force, right? Let's denote that torque as M. P here is the vertical applied force on the shaft. Here's a free body diagram for the shaft that will help us write down equilibrium equations. Let's go ahead and talk about this a little bit. Rj here is the radius of the journal, or in other words, radius of the shaft. And Rf, we'll talk about that in a little bit. And M here is the applied torque. A torque is applied in the clockwise direction on the shaft. P is the vertical force. And let's say the contact point has moved to this point from, of course, point A when we didn't have the torque. So why is it necessary for the contact point to move in that direction to point B, away from the vertical line passing through point C? Well, the reason is now we have a torque, M, right, applied on the shaft. So the force system here has to balance this applied torque. So let's denote the normal force at point B as N, and of course this normal force is going to go through point C, right? That's one of the radius. And then the frictional force at point B is going to be perpendicular to that, right? Tangent to the journal bearing, right? Say the resultant between these two forces, N and F, is capital R. Our objective here is to find the minimum torque that is needed to overcome the frictional force. So at that stage, F over N is going to be tan mu, and therefore this angle right here is going to be the friction angle phi, where phi is tan inverse of mu, right? The vertical force equilibrium equation written for the shaft tells you that this R must balance P. In other words, they must be equal to each other in magnitude and opposed in direction, right? Since P is vertical, R also must be vertical, right? In other words, the line of action of R is vertical, right? If I were to draw a circle that is tangent to that vertical line representing the line of action of R, that circle is what is called the friction circle. This angle right here is phi, right? The friction angle, and therefore this angle is also the friction angle, and therefore this radius right here is going to be Rj sine phi. In other words, Rf is going to be Rj sine phi. Now that R is off-centered, there is a moment arm to the line of action of that, and therefore R multiply that moment arm will be able to counterbalance the applied torque M. And this is why the contact point B has to move away from the vertical line. So let's go ahead and write down the equilibrium equations. Here they are. Defining my xy coordinate system like shown in this picture right here. This is the force equation in the vertical direction. This is the moment equation about point C. And of course these are all written for the forces acting on the shaft. These are fairly simple, fairly easy to follow, so I'll let you do that. We also said that the radius of the friction circle RF must be equal to Rj times sine phi, so let's put that in an equation as well. Combining these three equations, we get this expression for M. So this is the minimum torque that must be applied on the shaft in order to turn it in the beginning. If there are no other forces acting on the shaft, this will be the torque that must be applied on the shaft in order to keep it spinning at a constant velocity, right? Sometimes the applied force P may not be vertical. It could appear to be a little confusing. But it turns out that if you follow the same approach as this, the equations are identical. The core part of this approach is this friction circle. Note that in this approach, we are not really considering this normal force N and the frictional force F explicitly, right? These two forces have been kind of lumped into the resultant capital R. The line of action of this capital R is tangent to this friction circle, and all we needed in order to write down this moment equation is the radius of the friction circle. So we follow the same approach over here, and it turns out that you can avoid a lot of complications. Equations turn out to be exactly the same. Just to demonstrate the use of this equation in a numerical example, let's select these parameters for the key parameters Rj, P, and mu. The question here is to determine the minimum torque required to turn the shaft, and that's what this is, right? So first we go ahead and calculate the friction angle by this equation. Phi equal tan inverse mu, and we get a value of 16.7 degrees for that. We then simply apply these numbers in this equation. So P is 200 Newton, radius of the journal is 0.04 meters, and sine phi is 16.7 degrees. So I get a value of 2.29 Newton meter. So we need to apply a minimum torque of 2.29 Newton meter in order to initiate the rotation of the shaft, overcoming the torque corresponding to the frictional force. Earlier we said the analysis of a pulley that is spinning on a frictional shaft also falls within the same category as the journal bearings, right? So let's consider this pulley right here. There's a belt that goes around this pulley, and these belts are vertical in this particular case. The pulley has a radius RP. Let's assume that there's no slip between the pulley and the belt, and this pulley is rotating on the shaft shown by the black line here. A weight W is attached on one side of the belt, and we are pulling with a tension T on the other side. As you might recall from the analysis of flat belts, in problems like this, it's important to understand the impending motion. Let's say we are lifting the weight W by pulling on the belt over here. So the impending motion of the belt is going to be that shown by the green arrows here. The frictional force on the belt, between the belt and the pulley, is going to be resisting this motion, and therefore it's going to be opposed to this tension, right? It's going to be in that direction, right? And therefore T has to be greater than W. In other words, T will be equal to W plus the frictional force on the pulley, and therefore T will be greater than W. If that is the case, if I were to take a moment about point C for the forces acting on the pulley, right, the moment of T is going to be greater than the moment of W, right? The moment of T is simply T multiplied by the radius of the pulley, and moment of W is simply W multiplied by the radius of the pulley but acting in the counterclockwise direction. And therefore the contact between the pulley and the shaft will have to be on the right side of the vertical line passing through point C, so that the reaction right here, right, the resultant reaction will have a moment in order to counterbalance the differences in the moments due to T and W. The net moment due to T and W is going to be clockwise, and therefore moment due to the resultant R has to be counterclockwise. So qualitatively, this is the right location for the contact between the pulley and the shaft, not over here, not vertical. At the frictional limit, the angle between the resultant R and the contact normal will have to be phi, the friction angle phi, right? Next, since the tension and the weight W are both vertical, right, the resultant between these two is also vertical, and therefore R will also have to be vertical. In other words, the line of action of the resultant R is vertical, right? So this is my friction circle, the friction circle that is tangent to the resultant R. If this angle is phi, this angle is also phi, and therefore we can easily find the radius of the friction circle RF. RF is simply R shaft sine phi. With the objective of writing down a moment equation for the forces acting on the pulley, let's go ahead and define these horizontal distances. It's very easy to see. This distance is RP minus RF, where RP is the radius of the pulley, and this is going to be RP plus RF, right? So in this system, it's convenient to consider the equilibrium of the forces acting on the pulley rather than the equilibrium for the forces acting on the shaft. Here, our objective is to find an expression for the tension T. So the shortest way to achieve that is to take a moment about point A rather than point C. So that way we will not bring capital R into the equation. So here is the equation, and this leads to this expression for the tension T. Let's also write down what we said earlier about the radius of the friction circle. RF is Rj times sine phi, where Rj is the radius of the shaft. Just to demonstrate the use of this equation in a numerical example, let's go ahead and choose these values for the key parameters. We calculate a value of 11.3 degrees for phi here. We calculate a value of 7.84 millimeter for the radius of the friction circle, and then substituting the relevant numbers in this expression, we get a value of 432.6 Newton for the tension in the belt. This is the tension on the belt over here, right? So basically, the force needed to lift this weight of 400 Newton is 432.6 Newton. So it's a little bigger than 400 Newton. So the extra 32.6 Newton is the force needed to overcome the friction between the shaft and the pulley. Is there a big difference in the analysis if the impending motion is other way around? The answer is no. They're very, very similar. Let me just highlight the key differences and then you can go ahead and follow the details yourself. So this is the case if you are lowering the weight, right? So the impending motion is indicated by the green arrows here. So it's opposite to what we had over here, right? And in this case, T is going to be less than W, and therefore the torque due to the forces in the belt is going to be counterclockwise. So you need a countering moment in the clockwise direction. The contact force R will have to be on the left side this time. So the contact A moves to the left of the vertical passing through the center of the shaft. We will still employ the concept of the friction circle. The moment equation written for the forces acting on the pulley about point A leads to this expression for the tension. If you compare this expression with this one right here, you see that this is reciprocal of this. Using the same set of values for the key parameters, we end up with a tension of 369.8 Newton for this case. Remember, this tension is the force you need to apply in the belt over here, right? And we know T has to be less than W. So that's what we got. We got 369.8 in order to lift the weight of 400 Newton. What about in the same pulley system if the belt is horizontal over here? Does this make the analysis complicated? The answer is yes. It's a little bit more complicated. However, utilizing the idea of the friction circle, we can keep the level of complexity to a minimum. So here are the details of the analysis for the case where we are lifting the weight, where the impending motion is vertically up for the weight. And on the right side over here, we have the details for the case where we are lowering the weight. In these cases, the resultant contact force R between the pulley and the shaft is no longer vertical. But we don't know the exact direction. But we do know that the resultant has to be tangent to the friction circle in either case. Now visualizing a line passing through point A in that direction, right? The contact over here has to be on the right side of that line, whereas over here it's going to be on the left side of that line. This is because T in this case is greater than W, but T over here is less than W. Therefore, the net moment between T and W is going to be clockwise over here, whereas it's going to be counterclockwise. And therefore, the countering moment coming from the resultant between the pulley and the shaft is going to have to be counterclockwise here and clockwise here. Let's consider the XY coordinate system shown over here. X is taken to be horizontal, Y is taken to be vertical. It turns out that if you take the resultant R and resolve this into an X component Rx and a Y component Ry, the analysis is a little easier. Now considering the equilibrium of the forces acting on the pulley, here are my two force equations, one written along the X direction, the other one written along the Y direction. So we'll go ahead and take a moment about point A, which is the center of the shaft, instead of taking the moment about the contact point like we did in the earlier case. So these equations are fairly straightforward. I'll let you follow. In solving this equation, here's a little trick. So you find Rx from equation 1, right? Ry from equation 2. If I square Rx and square Ry, sum them up, what do we get? We get R squared, right? And therefore, R works out to be square root of T squared plus W squared. Now we substitute this expression for R in equation 3, and we have this equation. The only unknown in this equation is capital T, and that's what we are interested in, right? It's not too difficult to solve this equation. We're going to end up with a quadratic equation, and we'll illustrate the solution of that in a second in a numerical example. So here's a counterpart of this analysis when you are lowering the weight. Pretty easy to follow. I'll let you follow. So here are numerical examples, one for each case, just to demonstrate the details of the solution process. Choosing these values for the key parameters, I get a value of 11.3 degrees for the friction angle, 7.84 millimeter for the radius of the friction circle. So I'm going to take this equation number 1, square both sides of the equation and substitute numbers. That's what I have done over here. The square of t minus w is simply t squared minus 2tw plus w squared, right? So that's what I have over here. I brought rp to the right side and put it in the denominator here. The square of this term is just t squared plus w squared. And then we have the square of rf over rp. Simplifying this, I end up with this quadratic equation. There are two solutions for T. One of them is 425 Newton, the other is 377 Newton. So which is the correct solution? Well, for this case we know T has to be greater than W, right? And therefore 425 Newton is the correct answer because W is 400 Newton. For this case, for the same set of parameters, we end up with the same two values for T. So which of these two is the correct value for T? Well, in this case, T has to be less than W, right? And therefore 377 Newton is the correct answer here.